So basically, we want to establish a formula that can best predict your outcome given the deterministic inputs. And on top of that, we want to estimate how much the actual outcome is going to likely deviate from the predicted outcome. So the linear regression method is probably something you studied before, I guess. Which class did you take that actually touches linear regression?
6001.
6001. Oh, okay. So that early. Okay, cool. So let me just present linear regression in a very general sense. And that general sense is actually going to be very much generalizable to almost all statistical learning methods. That is, posing this statistical learning problem as an optimization problem. So what I'm really doing here is I want to construct a function form f, okay, within a particular class of functions such that my summation over all the samples goes from 1 to n, n being the number of samples, 200 in this case, of yi minus f of xi squared is minimum. All right. So here I use the square difference. There are several other variants that uses other norm of difference. Maybe you take the absolute value, for example, or in a different type of problems called classification problem, you don't minimize the difference between them, but like you look at the likelihood of look at the percentage of samples you are misclassifying as the function to be minimized. So basically you construct a objective function that is summed over all the data you have, and you look at what is how wrong am I in predicting the data. So linear regression is just a particular way of parameterizing these functions f. So if I only have linear regression is f of x is equal to ax plus b. So that's if you have a univariate linear regression, right? So this is univariate, and fx is just going to be a summation of, let me use j here, j equal to 1 to m being the number of variables, ai times x, aj times xj plus b, and this is multivariate. So the nice thing about this particular way of parameterizing the function is that when you plug in that formula into the objective function to be minimized, what kind of optimization problem does this generate? So first of all, is it clear what are the design parameters in this optimization problem?
In our case, it's the money spent on sales. So money spent on sales money spent in advertisement. Sorry, TV, newspaper.
Right. So here So the answer was the money spent on sales, etc. Actually, that's not what we are optimizing in this case. So here we are just trying to come up with an explanation of how much sales we get if we know how much money we spend on TV, newspaper, etc. A's and B's are the variables we want to tune to minimize this objective function. So basically the optimization problem is we are trying to find the function that best represent the data. Right, so if we already have a bunch of data like that, something similar to what we had before, the different A's and different B's are going to give us functions that are like this, maybe another one like this, another one like that. But all of them are probably not the best representation of the data. We want to have a line that goes like that, right? This would be a better representation of the data. And how do we quantify this is better representation of the data? Is the closeness, right? So this yi minus f of xi, this red line is f of xi. And yi is the black dots. So the difference between them are these. So this is the difference, this is the difference, another difference, another difference, another difference. The difference is basically the distance from the data to the prediction generated by the red line.
Usually in linear regression, the distance is measured to be like this, or distance is measured to be like this?
Good question. Is the distance vertical or is the distance perpendicular to the line? If you look at this formula over here.
It's not perpendicular.
It's straight, yes. This is actually true for almost all statistical learning methods.
Isn't it more accurate if we have it?
Is it more accurate if we have it perpendicular? It depends on what do you use to quantify more accurate. I think the classical way of quantifying more or less accurate is actually that, right? It's basically if I give you a set of control variables, you give me a prediction, and I'm going to look at how your prediction actually deviates from the real world. That's how usually we quantify the accuracy. If you try to minimize the distance to the line, I can imagine there might be a situation if the data is very vertically, lies in a vertical column.
Where it would be more accurate to like have the line perpendicular to have it just vertical column. I can't imagine.
Right. And also think of physically what that means. Physically what that means is that each data you have is assumed to be actually a real world data. It's actually assumed to be exact, right? It's actually reflective of the real world. What is wrong is your model, right? So it makes sense when you consider all the uncertainties to be in your model that you measure your misprediction, which is the difference in the y-axis. There is actually a different scenario on which measuring the straight perpendicular distance might make more sense. Is that if you know that the real world, the real response function actually is a straight line. But when you are collecting data, the data collection process might have an error both in the x and y axis. Then it makes more sense to minimize the perpendicular distance.
I'm just thinking of a case where we have these points, but where we have a different point which is really far away, but far away in the x direction. So if you subtract at that point the y of this from the y of the line, then you would get like a 0 difference. So it's minimal. But the x difference is huge. So in that case, the perpendicular shows you the difference.
I didn't understand you. So you're saying I have a point very much here?
Yeah, but same y is the line at this point. So if you're subtracting y of this point from the f of xi at this point.
Like here, right? I'm having a huge difference. But even if I look at the closest distance to the line, I also get a pretty big distance.
Yeah.
Right. So anyway, so I think like if you assume the data to be accurate, looking at the y-axis, the difference in the y-axis is a more reasonable way to quantify accuracy. If you actually know the data you collect is actually very noisy, both in the x and y direction, then you may consider looking at the perpendicular distance, right? Because then you are then you consider your red line to be the truth. It's just the data you have is actually noisy. So most of the situations, at least I've considered, is that your model is probably not going to be the truth, and the real world is the data you collect is actually a lot more accurate than the model you can construct.